Okay, so my name is Moris Zucca. I live in Trieste and I've been working there for RTL Italiana for the last 9 years. We recently changed names, as you probably heard, to SimCorp Italiana. I've been a developer on our main software solution. It's named Sophia. It's a financial software for insurances. However, today I won't be speaking about Sophia. I'm sorry. Today I will be showing you a bit of software-defined radio, starting with the definition and a brief history of software-defined radio, and especially of the so-called RTL software-defined radio. I will show you how these devices, these small devices, can be used under Windows, how to connect them to the Dyalog APL interpreter, and I'll show you a couple of applications, the FM radio and this small garage opener that actually opens my garage at home. And I'll end up with some more ideas that can be realized with this device. So what is a software-defined radio? In a traditional radio, all the components are traditionally made by in a hardware fashion. And so the modulators, filters, they are all small hardware components. However, you can achieve the same result as in a traditional radio if you sample the original signal, get out the raw signal from the electromagnetic waves, and convert it, filter it, demodulate it, use it using software. And that's what we call software-defined radio. SDR as a concept has existed for as long as computational power allowed it, since computational power allowed it. However, if you want to modify your data, you first have to obtain this data. And receivers that would work in a wide range of frequencies were expensive, as you can see in the picture, not very portable. And this was the situation until something else happened. About 15 years ago, devices like this started being sold on the market. They are used to watch digital television on computers. They are very small, very cheap. I actually wouldn't recommend buying the smallest one because it tends to get a bit hot. However, this one is also very portable, very cheap, and great. I wouldn't be speaking about them, however, if something else didn't happen. In 2010, Eric Fry, while trying to develop Linux drivers for this device, discovered that a particular group of these devices, all those based on the RTL-2832U chip, when receiving in radio, either in analog mode or digital mode, were actually outputting the raw signals, and the software provided with the device itself was in charge of demodulating and filtering the signal and obtaining sound from it. And that started the development of more software that now brought us to have this small branch of SDR called RTL-SDR, and I call it RTL-SDR generically because it's a term for many designs based on the same chip. They differ in the tuner because they can have various many different tuners, and the tuner defines the frequency range that they can achieve. My device in particular has the RI822 820T chip that I like particularly because it has a very wide range and no hole in the whole range. Other than the frequency, the other defining specs are the sampler rate that this device can achieve, that goes up to 3.2 million samples per second. However, at this sample rate, you have some signal loss. So 2.6 million samples is the highest achievable sample rate with no signal loss. The signal itself is composed of two 8-bit precision signals, and we will later, I'll show you a couple of demos. I will combine those two signals in a single complex number. So we'll have a single complex signal, and this way of sampling the original signal is very convenient because it can be shown that it allows to demodulate every kind of modulation. Under Windows, there are a lot of software solutions available. Many of those are based on the RTL-SDR DLLs. It's an open source library by Osmocom. And I'm telling you that because that will be also my approach. So I will be using those libraries to connect to this device from the Dyalog. And connecting it is very easy. The only thing you have to pay attention to is the driver that Windows associates by default to the device. That's usually not the one you want. That's the screenshot of my on my computer when I first connected the device. Zadig is an open source. I don't know, it's open source, but it's free. It's a free software that you can use to change the original drivers that Windows applied to the device that were correct for Windows probably, but are not correct for us. We need the WinUSB drivers because the RTL-SDR libraries themselves are built upon that. Other than that, you just have to download the DLLs from the Osmocom website, save them in a folder that's part of the system path, and use them in Dyalog. And I'll show you a quick demo of the device connected. It's here. Okay, first time initializing the device. In this case, I have only one device connected to the USB port, and however, I could have many of them, and I'm choosing based on the product name which device I'll be using. Now that I've connected to the device, I can see that the tuner is really the one that I told you before, the R820T. The starting frequency is of course 0, but we can set it to another frequency, and now the frequency is correctly set in the device. Same thing for the gains. These are all the gains that are available to the device itself. We can set it to 36.4 decibels, and the setting was correctly understood. The first thing before reading each read operation on the buffer is to reset it, and no errors. The length is the expected one, and the output is in the range of 8 bits, 8 bits numbers. Okay. So now that we have these raw values, we can start applying some modifications and try to obtain something usable. I will show you this subset of modifications available, because these are almost enough. They are just missing the demodulation part, but they will be enough to later show you the first application, the frequency demodulated, the frequency demodulation of the FM radio. So. Yeah, I'm trying. Okay. And move everything. Okay, so frequency, exemplar rate, time, some helper functions. And actually, I must say now that I'm not using the device itself. I'm using a pre-recorded signal. I recorded it at home because you never know what you will hear to. So, however, this is the same. Once I did this command, I saved whatever I got to a native file, so it's the same output I would get normally. So as I told you before, I'm first converting it to a complex signal, and this is, no, it's showing on the other monitor. This is the frequency distribution of the signal we read, and we can try to obtain a spectrogram of the signal, which means, and it's of course here. Okay. A spectrogram is the evolution of the signal, represents the evolution of the signal over time. So we have time in the horizontal axis, frequency in the vertical axis, and a color code that represents the height of the signal on that particular frequency. And you can see that, as expected, the signal is changing over time, but it's centered around 90.5 megahertz. Okay. We can move the signal, and we can move the plot, of course. So I moved it by 160 kilohertz, and you can see that it moved by that amount to the right. I will do the same to the left. Where is it? So it's here back again around the center. And then I can filter it. The filtering operation is, I've used the simplest filter actually. It's just one that given one sample limits how much the other sample can be far away from that one. And these are the effects of the filtering. So as you see, the peak in the center is stayed in the same place, but all the signals that are far away from the center have been drastically lowered. And lastly, we can see what's downsampling. Downsampling means that from sample rate of 1 million samples per second, we pass to 200,000. And this is a very simple operation because we are just choosing every fifth element of the array. But the effects are interesting because because we are losing all the high frequencies. So whatever was on the right and on the left, we don't have a way to get it back. We just focused on our center signal. Okay. And now we can see the first application of what we just saw, the FM radio. FM stands for frequency modulation, or frequency modulated radio. And we can see on the right a nice picture, a nice GIF I took from Wikipedia, where you can see that when the original signal is low, the frequency in the frequency modulated signal is lower, and the opposite, when the signal is high, the frequency is higher, but the amplitude of the signal itself stays unchanged. This is in contrast with amplitude modulation that you can see in the middle row, where the amplitude of the signal reflects the signal itself, the original signal itself, while the frequency stays constant over time. Okay, let's see a demo. As before, these are the frequency, sample rate, and time that I've used, but the signal is pre-recorded. I'm converting the two signals, the couples, to a complex form. The graph of the signal. The first operation we have to do is filter and down convert to 140 kilohertz. That will allow us to just focus on the middle signal. The filtering is the most complex operation in this code. And this is the actual demodulation. So just computing the difference between two signals, between two samples, two consecutive samples, gives us the instantaneous frequency of the signal at that moment. And then we must convert again to sample rate, to a frequency that we can put on to, just let me see, okay, that we can give to the speakers. 44 kilohertz in this case. Yes, just one more thing is that there is this effect sometimes. It's called DC offset, where the signal is centered about something lower than 0, but that's very easy to correct, of course. It actually makes no difference for the speaker itself, but it might for some applications. And I hope. 5 seconds of radio I recorded at home. It works. Okay. The second application is this little tool. It's my garage opener, which is actually sends signals over radio frequency at a frequency of 868 megahertz. It's written on the back side of it. And that was the only information I've had about this device. I had no manual, nothing about it. And so later, what I'm telling you now is something that I discovered later while listening to what the device sends actually. And I discovered that it's an amplitude modulated signal and it's a digital signal. And so I thought it would be a nice second application because it's in contrast with the first one, where the first one was analog because it has sound and frequency modulated. So frequency is the one I told you before. Sample rate, again, 1 million samples per second. The signal is pre-recorded. In this case, it's particularly important because you have to find where the signal starts. It takes a bit of time. 4 million samples, because we are getting 2 samples per each reading. Too complex becomes 2 millions. And this is what I first saw when I recorded the signal. We have the number of samples in the horizontal axis that it's correlated to time. So as the signal evolves over time, you can see that there are regions where the signal is very high, very strong. It actually gets cut up here because I was keeping the opener very close to the antenna, so it overflew sometimes. And there are regions where the signal is very low. And these are the characteristics. Yes, one more thing is that the frequency for the whole time is constant. And those are the characteristics of amplitude modulation. So if we suppose that it's amplitude modulation, we can take a look at the model of the signal, of the digital signal. And this is what I saw when I look at this. Okay. So we have a starting region where the signal is constantly high, and another region that's probably just an initialization of the device, and the second region where there is a lot of activity. So we can zoom to this second part and see what's going on there. And this is the start of the second part, where the activity is made by this. The signals are going up, and then they are 0, and then again to 1, 0. We have also this high frequency component, which we are not interested in. So we can just put a threshold over 100 and see it more clearly in this way. And this is our digital signal. It has a starting part with 8 couples, 1 zeros, then a longer signal that's probably indicating that there are 4, well, more than 1 ones, then some zeros, and again. There are 15 peaks here. We can count them. 15, just with enclose. We can see the how many samples are in each group, and we can take the minimum or a mean size for the sample to see what if the signal is just one value, one true value, or more than one. In this case, for example, this is the wider range, and we have that this is 4 ones. So for this first region that we zoomed in, we have this as the digital signal. We can do the same for the whole signal, and they are about 2.5 kilobytes, no, 2.5 kilobits of data. I don't know the content of the data itself. It doesn't matter. It was not in the scope of this work, and it's also encrypted. I think it changed these kind of devices change the key at each use, so it has really no meaning trying to decrypt. However, it's interesting that in the whole signal, this particular group of bits, so 4 ones and 4 zeros, is repeated about 7 or 8 times at constant length, so it's probably the signal being retransmitted. One last thing I wanted to show you about the signal is that the original signal was probably a square waveform, but we had that high frequency part in the ones. So we can try to filter it and see what's the effect on them. And so you see, this is the high frequency part. If we filter it, we get that it gets lowered. The peak stays as where it was. With this particular filter, if we get a window too big, however, we get undesired effects. In this case, filtering wasn't really important because the signal was clear, we could just put threshold. However, in other applications, it might be important. Just a word on transmission, because this device allows just to receive signals. There are other devices that allow also for transmission. However, there are stronger legal constraints, so if you want to try and use them, read the laws of your country. Unless you want to get in trouble. These are some other interesting ideas. Some of them I'm trying myself. I'm trying at the moment to receive and convert RDS transmission. However, these are very interesting ideas, and I put them on the list here along with the protocol of each one and the frequency at which they are sent. And you can see that all the frequency are in the range of the device, of what this device is capable of receiving. There are other very interesting ideas, and you should check the RTL-SDR website for more. And the last slide about what made me try this device and see how it works. Of course, everything is based on curiosity. I wanted to see what the radio was like. The picture I wanted to add to this slide is taken from the Discworld series. It's a series of books by Terry Pratchett, where he describes the world of Discworld, where magic interacts with normal life. And there is this scene that I like particularly, where a tourist, the first tourist of the Discworld, goes around taking pictures with this small box, and a mage that is accompanying him, that is guiding him around, is amazed at how this small box, with technology he never saw before, how it works. He read, of course, he's a mage, he knows a lot of things about how the world works, read a lot of books, and he thinks that maybe light going through some lenses is entering the box, hitting the surface on the other side, and maybe there's a surface treated with some chemical product or something that stops light in place, changes the color. Basically, it's how the camera works in our world. However, one day he opens the box itself, and inside there's this little imp drawing very fast, very quickly, whatever you show him. And that was to say, it's all good reading and seeing from books how things work, or having it explained by others. However, opening the box itself and seeing how it works is a totally different experience. And this was the opportunity for me to see the radio just in this way. And that's it. Thank you very much.
That was fascinating.
Have you been able to decode audio signals in real time, or you used some sample of some length and then decode it offline and then produce the sound?
The second. So I'm reading the signal, I'm listening to it, saving it, or either in memory or on a file, and then decoding it afterwards. I should be able to do it also in real time. However, the most difficult part of this process is the filtering, because well, the first time I tried filtering it for 5 seconds of sample, it took me 10 seconds to filter it. So that might be something difficult. However, that's just the way the filter is written. It could certainly be improved. So it should be done.
And second question, have you thought about automatically decoding some CW radio signals, which is Morse codes and so on? Perhaps it's a good idea to monitor everything that is in air. In this, I believe it's 13 to 15 megahertz. You can easily be able to do it.
14 to 15 megahertz.
Somewhere there.
Yeah, well, this device goes up to the lower bound is 24 megahertz, so it doesn't go up to that. However, there are projects. Maybe it's already possible to do it to go up to well, down to 100 kilohertz in direct sampling mode, where basically the chip is connected directly, bypassing the tuner at all, connected to the antenna. So it might be possible to achieve these frequencies, and once achieved, yes, I don't see any difficulty in doing something like this.
I think this was a fun and very different way of using Dyalog APL, and I congratulate you on the projects that you worked with. If we take your garage door opener, I assume you now have the unclonable garage door opener in Italy. But if we go back and look at the FM radio signals, I was wondering, you obviously demonstrated that works for listening, but are there any ideas or plans to have a commercial implementation of what you've done, working with somebody else who produces a device?
Well, this was just a hobby for this summer. It was something, as I told, that I was just interested to see how it works. I don't know, maybe.
Might be a good idea to find a hardware manufacturer who would like to use it.
Well, the Raspberry Pi has a Dyalog on it, so why not?
I'm curious about the fact that you say that you're able to capture both the real part and the imaginary part of the signal. How does that work physically?
This is not the complex part. The complex signal is actually just a representation. It's a very a nice representation that lets me work nicely with complex numbers. The way to receive the signal, what will be later the complex signal and the real signal, is just to read it before even applying the tuner. It's actually just a part that tunes down any frequency from the range you want down to 0. So before applying that modification, the tuner reads the frequency at a quarter of phase difference. It's the same signal, and then waits for a time to get the quarter of phase difference, and reads another signal. And those are then brought down to 0 together. So you have actually, let's say you can split the original signal in a cosine wave and a sine wave. And the sum of those two gets you the original signal.
But it's physically measured, or is it extrapolated?
No, it's measured just by applying a delay to the original signal. Even in other applications, the delay is applied to the same signal where you don't work on samples. In this case, they are samples, but you can do the same thing, the same kind of work on analog signals. And in that case, with hardware, you just delay the original signal by a quarter of a phase.
Okay, so you rebuild it, you don't physically measure it, right?
You measure the same signal twice.
Okay. Okay.
Yes.
Thank you.
I've heard of quite a number of applications of complex numbers, but this is the first time I have heard one. Thank you.
And yes, Nick, I did notice the complex numbers again. Okay, you brought us back on time. Thank you very much.
Thank you.